In today's lesson, we are going to introduce transformations. Now, this is going to be a little bit of a longer lesson because we do have to cover a lot of the basics, but it is going to be an important lesson because we do revisit these concepts, or we do need to understand these concepts as we go through the next couple lessons as well. So don't worry if it's a little bit long, or if we have some trouble with some of it, because we will be revisiting it. But a lot of the core concepts, we want to make sure that we really take the time to understand them, because we are going to see them come up in every lesson going forward in this unit, as well as some other ones. So the first thing, because we're going to be learning about transformations, we are going to be applying these transformations or these changes to three main functions. And these are three main functions that we have looked at before. So the first one is f at x is equal to x squared. And this is our quadratic function. So we should be familiar with this one. We've dealt with it a lot in grade 10. We've dealt with it in this unit, in this course as well. We had a whole unit on the quadratic function. The next one, f at x equals square root x. This is our radical function, or square root function. The next one is f at x equals 1 over x. This is our rational function. So we've dealt with these functions in a sense already. We've dealt with radicals, we've dealt with rationals, or expressions, we've dealt with them already. The quadratic one we have dealt a lot with, so we should be really familiar with those. But we are going to be looking at them going forward. These are going to be the main three that we look at. Now, these three equations are for each type of function are considered the base or parent functions. And these are going to be what we look at when we look at transformations within the respective families. So when we're talking about transforming quadratics or radicals or rationals, it's going to be based off of these functions. These are kind of like the starting points of our transformations. So it is going to be important to know what these base functions are, because all transformations are going to be based off of them. Now, before we learn about what transformations are or how they apply, we want to make sure we know what the base functions look like. If we're going to be changing something, we need to know what it looks like originally. Right? So if we don't know what it looks like originally, we're not really going to be able to understand how we change it. So that's what we're going to look at first. We're going to look at the different functions, and we're going to look at just what does the base functions of each type look like. So the base function for a quadratic was f at x equals x squared, right? Regular quadratic, x squared. So our key points, we have x and f at x, which is x squared. So if I had, say, -3, -2, -1, 0, 1, 2, 3, then the y value, or f at x, would equal 9, 4, 1, 0, 1, 4, 9. All we did was took those x values, plugged them into the function, and solved. So if I plot those points now, I end up with a parabola, which we should know already because we've dealt with quadratics quite a bit. And we should recognize this shape, this U shape. It could also be an N shape, but this is our base function. This is what the original looks like. Without any changes, this is what our original parent or base function looks like. Moving on to radical functions, this was f at x is equal to the square root of x. So again, some key points: 0, 1, 4, 9, 16, 25. We could go on to 36, but we probably won't be able to find that on our grid. So right now, f at x, again, just plugging these values into the function. So 0 squared is 0, 1 squared is 1, the square root of 0 is 0, the square root of 1 is 1, the square root of 4 is 2, the square root of 9 is 3, the square root of 16 is 4, 25, it's 5, and if we wanted to, we could do 36, which is 6. Now I'm missing a lot of points on my x values. I'm jumping around just because I know if I'm taking the square root of a number, I should get, if I want to make it nice values, it's going to have to be a perfect square. So when I plot those points, 0, 1 and 1, 4 and 2, 9 and 3. Can't really plot the rest, but this is in general what my function looks like, right, for a radical function. For a rational function, again, our base function, we had said originally, f of x is equal to 1 over x. So when I plot my points, I just have to come up with x values and then plot them, or plug them into our function and solve. So we'll go again, -2, -1, we'll do -1/2, 0, 1/2, 1, and 2. So -2, so 1 over -2 is 1, -1/2, -1, 1 divided by -1/2 is -2. 0 is undefined, or error. And we get +2, +1, and +1/2. So let's plot these points. So -2 and -1/2, -1 and -1, -1/2 and -2. 0, there's nothing. At 1/2, there is 2. At 1, it's 1, and at 2, it's 1/2. So this is actually going to look something a little bit like this. Again, we've touched on this function before, so this shouldn't be entirely foreign to you, but we should also recognize that we do have what we call asymptotes. We do have asymptotes, 1 when x is 0, and 1 when y is 0. So that means the function will never reach a value of 0, and we cannot have a value of x at 0. So for this one, just as a side note, there is a horizontal asymptote, ASY, horizontal asymptote at y equals 0, and there is also a vertical asymptote at x equals 0. Basically, we have it. This is what our rational function looks like, right, with the two values that it cannot equal. Now that we've looked at what the base or parent functions are, now we can look at transformations. Now, a transformation is a change made to a figure or a relation such that the figure or the graph is shifted or changed in shape. So basically, we are changing the shape or location as well of our base or parent function. Now, the main types of transformations are going to be what we call translations, stretches, and reflections. So those are going to be the main types of transformations that we're going to do. Translation is just another way of saying that we're shifting or moving it. Stretching or compressing is like kind of like pulling it or pushing it in. And reflections is another word basically for flipping. Right? So we might flip our function. Now our general function, g at x, equals a f k bracket x minus d plus c. So this is our general function. Right? The f and the x, these two values or these two variables, these just represent f at x, which is our parent function or base function. So f and x don't represent anything. It's just another way to write the transformed or the base function. The A, K, D, and C are all parts of that we're changing or transforming. G at x represents the transforms function. So G at x represents the transform function. This f and x represent the parent function, right? The G at x basically means we take the parent function and we apply transformations to it. We do things to change it. And we're going to look at what each variable represents. And you might have looked at this already in grade 10, specifically with the vertex form of quadratics, but we will touch on what each variable represents. So first, looking at the changes to the y-coordinates or vertical changes. Right, so these are things that are going to change the vertical component of our graph or of our function. The first one we have is the c value, which is the vertical translation. So this c value is the plus c at the end. So in general, it would be g at x equals f at x plus c. So we're adding something at the end. Right? The graph of g at x, right, of the transform function, is a vertical translation of the graph of the parent function by c units. Another way to think of this is a vertical shift. Basically, if c is greater than 0 or positive, plus sign will be easier, positive, then the graph shifts up. If it is negative or less than 0, it shifts down. So if our c value is positive, we're moving our graph up. If it's negative, we're moving it down. The next component is the a value. This is the one that's at the very front. This is our stretch or compression, or our vertical stretch or compression. So the graph, right, our transformed function is a vertical stretch or compression of the graph, and the key term is by a factor of a. So by a factor of whatever the a value is. And we're going to be touching on that a bit when we talk about the reflection or the transformations. Here, there's three kind of situations that could happen or scenarios. If a is greater than 1 or greater than -1, we have a vertical stretch. So if it is a whole number greater than 1, we have a vertical stretch. If it is between -1 and 0, then it is a vertical compression. So this would be basically a decimal. So if we had a decimal value for our a value, it's a vertical compression. And if a is less than 0, we have a vertical reflection. Or we could say, in other words, we have a negative value. If we have a negative a, it's a vertical reflection, meaning we flip it. So you might think, okay, what does a vertical stretch mean? Vertical stretch would be if we took our base function like this, and let's just highlight it, and we stretched it. So that would be an example of a vertical stretch. A vertical compression would be the opposite. We kind of squeeze it together, and we can see that it kind of spreads out a little bit. So we make it very thin, or we start to make it wider. Thin, wide, stretch, compress. A reflection basically means the opposite. We just flip everything. Oops, work on this way. Is there an option? Doesn't seem to be an option. But a reflection just basically means that we flip it. So it goes like this. That would be a reflection. We flip. So stretch or compression, we just kind of give you a visual. Reflection means we flip. And it all depends on what the a value is. And now things to note, vertical stretch or compression means that the distance from the x-axis of each point of the parent function changes by a factor of a. So if the a value is greater than 1, that means it's going to stretch, or greater than 1 or greater than -1. That means the distance is going to be farther away, meaning it's going to have that vertical stretch. It's going to look very tall and thin. Right? If it's compressed, that means we're decreasing the distance, so it's going to make it kind of shorter or closer, or kind of like shorter and wider, you might say. And then reflection, we basically make all our y values negative. We flip it over the x-axis, reflect it over the x-axis. Now for the x-coordinates, or changes to the x-coordinates, so these would be our horizontal changes. So this is everything dealing with the x value. One, we have a horizontal translation or horizontal shift, and this is the d value. Now keep in mind, it's inherently negative in our equation, right? Or not inherently, but it's automatic. It's initially negative in our equation, right? So that means if d is greater than 0, it shifts right. If it's less than 0, it shifts left. Makes sense. Positive d goes to the right, negative goes to the left. Oops. However, because it's initially negative, it's the opposite of what we see. So it's the opposite of what you see. And actually, I'm just going to move that for here. So these d values are going to be the opposite of what you see. So if you see a positive d, that means you're minusing a negative, right? Because double sign minus a negative, right? If I had if I had x minus negative d, that becomes x plus d. And if I had x minus a positive d value, that becomes x minus d. So it's the opposite of what we see. Horizontal stretch and compression, this is the k value. So this is the value that will be in front of the x, between the f and the x. And this is a horizontal stretch or compression, and it's by a factor of 1 over k. Right? So it's slightly different. The a value we just multiplied our x or y value, by a. Here it's by a factor of 1 over k, or 1 divided by k. So if we have a compression, then that means our k value is greater than 1 or negative 1. And it's compressed horizontally by a factor of 1 over k, which we already talked about. If it is between negative 1 and 1, it's stretched horizontally. And if it is a negative value or less than 0, there's a horizontal reflection, or it's reflected over not the x-axis, the y-axis. So again, just as some reminders, greater than 1 or greater than negative 1, these are whole numbers. Between negative 1 and 1, we're looking for decimals. And when it's less than 0, it's negative, is what we're essentially referring to. So for what this might look like, so if I draw my base function, right, I'll stick with the quadratic because that was our first one. Horizontal stretch would be something like this. So this would be a stretch, making it wider horizontally. Compression would be taking it and bringing it in. So compression or stretch, compression, stretch, compression. And a reflection would basically be if I just kind of flip it over kind of an initial the y-axis. So if I had the y-axis here and I flipped it over, it would look something like this. Now with a quadratic, it might not be easy to see that flip, but that's the flip that we're talking about, going in this direction rather than this, which was the vertical reflection. So again, one thing to note, right? Again, the horizontal stretch or compression means that the distance from the y-axis of each point changes by a factor of 1 over k. I'm going to highlight that 1 over k, or that factor of 1 over k, because that is different from the vertical the vertical compression or stretch. And again, for a horizontal reflection, the point xy becomes the point negative xy. So we're flipping it over the y-axis. We're basically making our x values the opposite. Now, when we're dealing with transformations, we want to make sure that we do it in the correct order, because that will help find our new values. So when we're doing our transformations, the order we want to do it first is we want to do any stretches, compressions, or reflections first. So that means any changing by a factor or reflection, we want to do that first, and then we do our translations. So a helpful kind of pathway to follow or procedure, we start with our A value. Let me just change it a bit. We start with our A value, right? See if we have an A value that's changing. Then we move on to our K, then our D, and then our C. Right? So those are the kind of the process that we look through for when we're doing our transformations, or the order that we want to do them in. So let's take a look at some functions and list the transformations and the order in which they should be done to the base function or that parent function f at x. So I'm going to look at the first one. For a, g at x is equal to negative f at x. So I'm going to go highlight any of my transformations, anything that's happening to this parent function. The only thing I'm going to highlight right now is just that it's negative. Right? This is actually a negative 1. So that tells me, let me go back to the smaller one. So this tells me that there's a negative 1 in front, and if I have my parent or my kind of general form, right, g at x is equal to a f k x minus d plus c. This is the a value, so this is saying that a is equal to negative 1. And if I go back to kind of my handy little chart, or negative 1, not 1, go back in my notes, I know the a value, when it's a negative, it tells me that there is a vertical reflection. And that is the first and only transformation, I guess I should say. So just put a 1. So vertical reflection is our first and only transformation for this parent function. For b, I see two values, a 2 and a 1/3. Right? This is telling me that I have an a value equal to 2, and it tells me that I have a k value. Because it's the k value, that means it's 1 over k, which means it's 1 over 1/3, which means it's equal to 3. So here I have my my two values. So first, if we go back to that process in our notes, the first one was the a value. So the first thing we should do is a vertical stretch. Because it is a positive and it is a whole number, so vertical stretch, we could say by a factor of 2. And the second transformation is going to be this k, so it's a positive value, it's a whole value, so that means there will be a horizontal stretch, and we can say by a factor of 3. So this basically means for this, or for the vertical or the a value, essentially multiply the y values by 2. For the horizontal, we multiply the x values by 3. So that's what we mean when we're talking about a horizontal or vertical stretch. For C, I'm just going to go through, highlight where my transformations are going to occur, figure out what variables or they represent from that parent function. Right, so just scrolling back up, g at x is equal to a f, which is part of the parent function, kx, x is part of the parent function, minus d plus c. So here I have my a value, which is 3. No k value, but I do have a d value. And because it's a positive 2, I should remember that it's the opposite of what I'm seeing. So this is actually a negative 2. and then my C value, which is a -1. So that C value at the end, we don't worry about changing what we see as we see it, or what we see it as is what our C value is. So now our transformations. First one, we've dealt with this one before. Vertical stretch. Say by a factor of 3. So this is essentially saying, we'll write this down because this will help when we kind of start to actually draw these draw these change functions. So we multiply, we'll say x, or sorry, not x, y values, because it's vertical. Y values by 3. The second transformation is our d value. This is what we call a horizontal translation. Translation. And because it is a negative, that means it's left. We'll say 2 units. So another thing, essentially what we're doing to each value is x values minus 2. So whatever x values are, we subtract 2 from each one. And our third transformation, the C value, is a vertical translation. It's a negative, so it's down, and down 1 unit. And the transformation is essentially the y values. We subtract 1, or we minus 1 from the y values. So that's what we're doing to each point, essentially, in red. And that's going to be helpful when we have to actually draw the parent, or the transformed function. So looking at some 2 other ones, right? So D and E. So I want you to try these on your own, right? So try these on your own. Think about, or what I would suggest first is highlight any of the numbers, and then go back to that general function and think about, okay, what transformation are these representing? And we'll come back with an answer. So coming back to our 2 final questions, or 2 final examples. Looking at D, g at x equals 1 over 4 f2, and then x times x minus 1. So that means we have an a, k, and a d value. So for our a value, it's 1 over 4. Our k value, 1 over k, becomes 1 over 2. And our d value is a positive 1. Remember, opposite of what we see. So this means in an order of transformations, we have a vertical compression by a factor of 1 over 4, meaning we multiply our y values by 1 over 4. We have a horizontal compression because it's a 1/2, but horizontal compression by a factor of 1 over 2, meaning we multiply the x values by 1/2. And then we shift, our final transformation is we shift right. Now I changed it because you can also write the horizontal translation right. You can just basically say shift right if you'd like. So shift right 1 unit, meaning we add 1 to our x values. You can see, and you can see by looking at what we do to the values, why we deal with the translations, or sorry, the stretches, the compressions, and the reflections before the translations, right? Because what we're doing to the values, we're multiplying or dividing, possibly in some cases. We're multiplying by 1/2, it's the same as dividing by 2, but we're multiplying, which comes before the addition or subtraction. So we're almost kind of following BEDMAS by what we would do to the values. And for E, g at x is equal to 3f in brackets x plus 2 minus 1. So that means we have an a, d, and a c value. A is 3, d is -2, opposite of what you see, and c is -1. So our first transformation would be a vertical stretch by a factor of 3. We multiply the y values by 3. For the second one, we shift our left 2 units, our x values -2, And then our third and final transformation, we shift down 1 unit, or our y values are subtracting 1 or minus 1. So that was looking at the different types of transformations just by looking at the function. Now let's look at actually changing our function. Let's look at what the actual final product is going to be. So here we're going to list the transformations in the order that they should be done, and then we're going to use this graph of f at x to sketch our new transform function. So if I look at my transform function, g at x is equal to f at x plus 2, I have one variable in there, or one value, this plus 2. That means I have a d value of -2, opposite of what we see. And this means that we shift left 2 units. Or you could say x values -2. So to draw that, I'm going to take all my x values and shift them to the left 2 units. So I'm going to start here. This point is going to go to the left 2 units, so it'll end up here. This one will go to the left 2 units, 1, 2. This one will go over 2 units to here. This one will go over 2 units to here. Now I'm just basically almost going to connect the dots. It doesn't have to be perfect, right? We're just sketching what the transform function is going to look like. And there's my transformed function g at x. And I can see that the entire thing is shifted to the left 2. The next one, b is g at x is equal to negative f at x. So I only have one transformation here, this negative in front. This means that a value is a -1. This means that we have a vertical reflection. So when we have a vertical reflection, the y values multiplied by -1. Basically, we reflect everything over the x-axis. So if this is our x-axis here, all the values are on the opposite or flipped over that. So this first point up here, this top one here, because it's 2 above, when it gets reflected, it's 2 below. This one's 3 below, so it becomes 3 above. 2 below, 2 above, and same thing for the last one. So now when I draw it, there is my transformed function. So it's flipped over that horizontal axis. For c, g at x is equal to f at x plus 3. Again, I only have one transformation here. This plus 3 is outside the bracket. So this tells me that it is a c value. So my c value is equal to 3. This means I shift up 3 units, or my y values are adding 3 to them. So the translations are a little bit easy because it's just moving your points up or down or left or right. So I'm going to look at each point and I'm going to move it up 3. So start here, go up 1, 2, 3. That's my new point. Up 3, and up 3. Connect the dots. And there's my transform function g at x. So again, nothing too complicated with the kind of reflections or the shifting up or down. Those ones should be relatively straightforward. Now when we get the horizontal translations or the vertical horizontal stretch or compression and the vertical stretch or compression, that's where it gets tricky. So I have 2 transformations here. I have a k value, or I guess technically a 1 over k, which is 1 over 2. And I have a c value of -1. So this tells me that first I have to do a horizontal compression by a factor of 1/2. This basically tells me that I multiply the x values by 1/2. And lastly then, for my y values, I have, not my y value, well, yes, my y values, but jumping ahead of myself, I have a c value, which tells me that I shift down 1 unit. Or I take my y values, I subtract 1. So when we're dealing with multiple transformations, it can be a little bit hard to draw what our transform function is going to look like. And this is where it might be helpful to kind of do some form of what we call kind of mapping notation. Right? So if I have my parent function, f at x, if I create a table of values for it, x and y, I can see that I have -3 and 2, -1 and -3, 1 and -2, and 3 and -2. That's my parent function. Now, it's going to get transformed. It's going to get transformed to g at x, or my transform function, and that's going to change the values. And we've been tracking kind of what happens to each value. Well, in this case, we've mentioned that we have to multiply our x values by 1/2, which is the same as dividing our x values by 2. And our y values, we are going to subtract 1 because we're shifting everything down. So now that I have this kind of new mapping notation or new kind of transformations that's happening to each point, I can apply those transformations. So for my x value, for my first point, I'm going to divide it by 2. So 3 divided by 2 is -1/2. Sorry, -3 divided by 2. For my y value, I'm taking a 1 away from it. So 2 minus 1 is 1. So this point of -3, 2 now becomes -1.5 and 1. So -1.5 for the x value and 1. So that is my new point, or new starting point, you could say. For the next point, -1 divided by 2 is -1/2. -3 minus 1 is -4. So I'm going to plot that point now. So -1/2 and -4. For the next point, 1 divided by 2 is 1/2. -2 minus 1 is -3. So 1/2 and -3. And for the other one, 3 divided by 1/2 is 1.5. -2 minus 1 is -3. So I have a point at 1.53. Oops. Right there. So now when I connect the dots, it's going to look something like this. So that is my transformed function now. And we should see that it is shifted down 1, but it's also compressed horizontally. And if we kind of take this and we kind of expand it, we could see that if I really wanted to, if I really wanted to, I could probably almost overlay this. There we go. Right, so there's my original function. Now, I've compressed it horizontally by a factor of 1/2. So basically I've shrunk it in, or I've compressed it. So all my points are compressed by 1/2, which we can kind of see happening there. And I've shifted it down 1 to there. And we've done the same thing with our points and mapping it. So if we do get complex transformations or a lot of transformations, we can always kind of use this idea of this mapping notation. Let me put that in there. Right, we'll call this this idea of writing out the points, call it mapping notation. And also we could call these points image points. So the points on our image or our transformed function, we call it image points. So again, different ways to do it. I would say when you start dealing with the compressions, the stretch and compressions, it's going to be a lot easier to use this kind of image point idea or this mapping notation rather than trying to just draw it out, similar to what we did with some of the other ones when it's just shifting it up and down or reflecting it. But again, these transformations are going to be the same regardless of the type of function that we look at. So we've just looked at this general f at x function, this kind of maybe like Big Dipper type looking figure. But we are going to be looking at these same types of transformations with those three basic functions, the quadratic, the radical, and the rational. So it's important that you know what the a, k, d, and c variables in our transformed function represent, how they change it, because we're going to be looking at those same variables or those same transformations with those three main functions.